The Fundamental Manufacturing Processes video series, examining the tools and techniques of precision manufacturing. This program explores the fundamentals of brazing and soldering. Brazing and soldering are joining processes that use heat, filler metal, and usually flux to produce a metallurgical bond between materials. Brazing and soldering are similar in process, with the main difference being that brazing is performed using a filler metal having a melting or liquidus temperature above 840 degrees Fahrenheit or 450 degrees Celsius, while the filler metals used in soldering have liquidus temperatures below 840 degrees Fahrenheit or 450 degrees Celsius. Both brazing and soldering operations are performed at temperatures below the melting or solidus temperature of the base materials being joined. For this reason, properties of brazed and soldered joints are typically not the same as those of the base metal. The filler metals for both brazing and soldering are typically held in or distributed between closely fitted, interfacing or faying joint surfaces by capillary action. Capillary action occurs because the atoms of the liquefied filler metal have stronger attraction to the base metal's atoms than to their own. When this attraction occurs between two surfaces, the liquid evenly distributes itself. The spreading of a liquid through capillary action and adhering in a continuous layer to a solid material is commonly referred to as wetting. In many cases, flux is used to assist in the proper distribution of filler metal. The primary purpose of flux is to inhibit the formation of oxides and other undesirable materials within the molten filler metal and on joint surfaces during joining. Flux also promotes wetting joint surfaces by lowering surface tension during joining. Flux has a lower attraction to the base metal's atoms than does the filler metal. As the filler metal melts, it pushes out the majority of the molten flux and adheres to a clean, oxide-free surface. Flux residue is corrosive, so its removal after joining is essential. Soaking in hot or warm water is a common procedure, but mechanical cleaning may sometimes be necessary. Brazing and soldering operations are used for many industrial applications, including manufacturing automobiles, aircraft, appliances, tube and pipe, and electronics. An important aspect of both brazing and soldering is joint design, with the primary joint types used including the lap joint, the flanged lap joint, the butt joint, and the flanged butt joint. Joint preparation is essential in brazing and soldering. All dirt, grease, and paint must be removed from joint surfaces prior to joining to ensure full capillary action of flux and filler metal. Joint surfaces are typically cleaned using chemical or mechanical methods. Chemical cleaning methods include the use of petrochemical solvents, alkaline cleaning agents, electrolytic cleaning, and salt baths. Mechanical methods of cleaning joint surfaces include grinding, machining, sanding, wire brushing, and blasting. Once cleaned, assemblies are prepared for joining using either brazing or soldering processes. Brazing is often selected over other joining methods such as mechanical fastening and welding for many reasons, such as inaccessible joint areas, that cannot be joined using welding processes can be joined using brazing. Thin-wall tubes and assemblies damageable by welding can be joined using brazing. Multiple joints can be brazed at one time, and the process is readily automated for high production rates. Brazed joints can be ductile and corrosion resistant, and brazing can join dissimilar metals and non-metallic materials. Most ferrous and non-ferrous metals, plus carbides, such as tungsten carbides and cermets, can be brazed. Brazeable ferrous metals include plain carbon steels, low and high alloy steels, stainless steels, and most cast irons. Brazeable non-ferrous metals include aluminum, copper, bronze, brass, nickel, titanium, and their alloys. Fluxes for brazing typically contain fluorides, chlorides, borax, borates, fluoroborates, alkalis, wetting agents, and water. Fluxes are available in many forms, including liquids, pastes, powders, and preforms. Various methods are used to apply brazing flux to the joint, with the most common being brushing, spraying, or dipping. Fluxes, when heated, can be toxic if inhaled, so proper safety precautions must be taken during their use. The type of filler metal used for brazing depends on the base metal or materials being joined. The most common filler metals include aluminum silicon, copper, copper phosphorus, magnesium, silver, and nickel alloys. Filler metals each flow within specific temperature ranges and are available in many forms, including wire, foil, paste, powder, and preforms. Filler metals commonly have a significantly different composition than the metals being joined. Proper filler metal selection is important to avoid problems such as galvanic corrosion or formation of brittle intermetallic compounds within the joint. Typical brazing joint clearances for good capillary flow and joint strength range from 1/1000th of an inch, or 25 thousandths of a millimeter, to 5 thousandths of an inch, or approximately 13 hundredths of a millimeter. Common methods of brazing include torch brazing, furnace brazing, dip brazing, and induction brazing. Torch brazing, which is also commonly referred to as flame brazing, uses oxy-fuel gas. Flux is typically applied to the joint before heating, and the brazing filler metal is deposited as soon as the joint is up to temperature, but the filler metal can also be placed in the joint along with the flux prior to heating. Torch brazing is performed manually, but can also be automated as a production process. Furnace brazing is the most commonly used production brazing technique. As the name suggests, the process is carried out in a furnace with assembled components cleaned, preloaded with filler metal in or at the joints, and then fixtured for proper positioning during brazing. Both batch and continuous conveyor furnaces are used for brazing. Batch brazing operations use retorts or cold wall vacuum furnaces. Prepared assemblies are stacked on trays, loaded into the furnace, and then brought to temperature, brazing all assemblies at the same time. Batch brazing furnaces are commonly used to join assemblies having complex joint designs. Continuous brazing uses a conveyor belt or rolls to take the assemblies through the brazing furnace. These furnaces have multiple zones for preheating the assemblies, high heat brazing, and cool down. Continuous conveyor brazing is used for high production runs, typically on small parts with simple joint designs. Furnace brazing is most commonly performed in furnaces having various special protective atmospheres or in vacuum furnaces. The use of furnaces with special protective atmospheres or vacuum furnaces eliminates the need for fluxing, precluding the need to remove flux residue after joining. Protective atmospheres or vacuum furnaces are also used to prevent oxide formation of reactive, refractory, or high-temperature metals, and to control carbon content, preventing the decarburization of steel. In dip brazing, assemblies may be dipped in a molten filler metal bath, but are most typically immersed, heated, and brazed in a molten chemical bath. The cleaned assemblies are prepared with filler metal placed in the joints. The assemblies are then preheated and then dipped in the molten chemical bath, which serves as the flux and melts the filler metal. Dip brazing is commonly used for dipping complex assemblies of various thicknesses and is performed at temperatures close to the melting point of the base metals. Fixturing the assemblies is important. Assemblies can be self-fixtured by crimping or swedging, or mechanically fixtured by using heat-resistant external springs and clamps. Once the assemblies are raised from the bath, they are rinsed in hot water to loosen flux residue. Assemblies then undergo additional cleaning steps to ensure complete flux residue removal. Induction brazing uses an inductor coil or coils to induce an AC or alternating current in an assembly. As this current flows within and around the assembly, heat is generated from the resistance of the assembly to the current, bringing it quickly up to brazing temperature. Inductor coils can be made of copper tubing or machined from copper block and are shaped to maximize current transfer to the assembly being brazed. To prevent melting, inductor coils are commonly water-cooled internally. Coils must be closely coupled to the assemblies being brazed. The closer the coupling or gap, the more efficient the operation. The gap also can be used to control the rate of heating of different parts in the assemblies. Soldering processes are some of the oldest methods used to join metals, with most producing an intermetallic type metallurgical bond between the solder and base materials. Soldering offers many advantages over other fastening processes, such as multiple, reliable joints can be made quickly and economically, evaluated visually, and easily repaired if necessary. The low temperatures employed for soldering minimize distortion and heat damage to the components being joined. Dissimilar materials, such as ceramic to metal or glass to metal, may be soldered, and soldering processes are easily automated for high production. For these reasons, soldering is used extensively in the electronics industry. However, soldered joints have limited mechanical strength compared to brazing, welding, and mechanical fastening. Soldering is used to join a wide range of metals. Among the more solderable are low-carbon steels, copper and many copper alloys, lead and lead alloys, tin and tin alloys, and zinc. Fluxes for the range of solderable materials are generally classified into three categories: inorganic acid fluxes, organic acid fluxes, and rosin-based fluxes. These fluxes may be solvent-based or water-based. Like brazing fluxes, soldering fluxes are available in many forms, including liquids, pastes, powders, and as flux cored solder. These fluxes are applied using many of the same methods as in brazing. Soldering filler metals, commonly referred to as solder, typically contain tin and lead, or tin, silver, and lead as the primary ingredients. Other solder compositions include tin zinc, silver copper zinc, and zinc aluminum alloys. Solders are available in various forms, with or without flux, including cakes or ingots, sheet, foil, wire, paste, and preforms. When heated, solder and fluxes can be irritating or toxic, necessitating precautions during operations. Afterwards, residues from corrosive fluxes are removed as required. To ensure adequate capillary flow, joint clearance for soldering operations typically ranges from 0.03 of an inch or 0.08 of a millimeter to 0.06 of an inch or 0.15 of a millimeter. Many soldering processes are similar to brazing processes, except they are performed at lower temperature. These processes include torch soldering, furnace soldering, dip soldering, and induction soldering. Processes unique to soldering include iron soldering and wave soldering. Iron soldering, using conventional soldering irons, is the oldest soldering method and is still widely used. Soldering irons have a copper tip mounted to a heat-resistant handle. The copper tip stores and transfers heat to the joint. Once the joint is up to soldering temperature, solder is applied between the iron tip and the assembly joint to melt and form the bond. Soldering irons are available in various forms and are commonly heated electrically, but irons may also be heated by direct flame or in ovens. Wave soldering is used for automated soldering of electronic components onto printed circuit boards. In wave soldering, the solder is lifted to the connection joints by one or more standing fountains or waves of continuously circulated fresh hot solder. At any given time, only a small band of the assembly is immersed in the wave, eliminating exposure of the circuit board to excess heat. A multitude of printed circuit board joints are soldered in seconds by wave soldering. Because the operation is fast, it reduces assembly warpage, as well as air, flux, and vapor entrapment during soldering. Wave soldering machines are available that flux, preheat, solder, and clean flux residue off the finished printed circuit boards while on a single conveyor transport. Let's review the material contained in this program. Brazing and soldering are joining processes that use heat, filler metal, and usually flux to produce a metallurgical bond between materials. brazing and soldering are similar in process, with the main difference being that brazing is performed using a filler metal having a melting or liquidus temperature above 840 degrees Fahrenheit or 450 degrees Celsius, while the filler metals used in soldering have liquidus temperatures below 840 degrees Fahrenheit or 450 degrees Celsius. The filler metals for both brazing and soldering are typically held in or distributed between closely fitted, interfacing or faying joint surfaces by capillary action. Capillary action occurs because the atoms of the liquefied filler metal have stronger attraction to the base metal's atoms than to their own. When this attraction occurs between two surfaces, the liquid evenly distributes itself. In many cases, flux is used to assist in the proper distribution of filler metal. Flux residue is corrosive, so its removal after joining is essential. Soaking in hot or warm water is a common procedure, but mechanical cleaning may sometimes be necessary. The type of filler metal used for brazing depends on the base metal or materials being joined. The most common filler metals include aluminum silicon, copper, copper phosphorus, magnesium, silver, and nickel alloys. Common methods of brazing include torch brazing, batch furnace brazing, continuous furnace brazing, dip brazing, and induction brazing. Soldering processes are some of the oldest methods used to join metals, with most producing an intermetallic type metallurgical bond between the solder and base materials. Soldering filler metals, commonly referred to as solder, typically contain tin and lead, or tin, silver, and lead as the primary ingredients. Other solder compositions include tin zinc, silver copper zinc, and zinc aluminum alloys. Many soldering processes are similar to brazing processes, except they are performed at lower temperature. These processes include torch soldering, furnace soldering, dip soldering, and induction soldering. Processes unique to soldering include iron soldering and wave soldering, which is used extensively to produce electronic circuit boards.